Okay. So last time, we just started 3.3 modeling with the systems of first order differential equations. So instead, with just one single first order differential equation, we have two or three or more differential equations in the system. We talk about isotope decay series. We talk about the predator-prey model for populations. Basically, if you consider the ecosystem of a fox and the foxes and the rabbits, then because the food chain, then the population of both foxes and rabbits will depend on each other. So then we have a system of nonlinear differential equations, but they are still first order if you look at the equations we're getting here. Okay. If X is the population of foxes and Y is the population of rabbits, then we can write down differential equation dx over dt equals x times negative a plus by, where a and b are constants. And another differential equation for population of the rabbits will be dy over dt equals y times d minus cx. I miss y here. Okay. So this model is called Unlucky Watera predator-prey model. Okay, it describes a food chain ecosystem. All right, so we will not solve these equations in this chapter. We don't know how to do it at this point, actually. But let's just see some solutions, for this model that solved maybe later. Okay. So suppose this system we have, the differential equations we have, or dx dt equals negative 0.16x plus 0.08xy, and dy over dt equals 4.51 minus 0.9xy. Again, x is the population of foxes, and y is the population of rabbits. Okay, so you can see, So that's a specific example for this predator-prey model. So A, B, C, and D are given in this example. Okay, so if you solve this system of equations numerically, then what you see is like this. The solution will be like this. If we look at the graph, figure 3.3.2, populations of predator, red, and prey in blue in this example. Okay, so what you see here is both of the predators, the foxes, and the prey, the rabbits, populations are periodical with time. You can see, and that really makes sense. So this is an interesting result. So the population do not change with time monotonically. They don't just increase or decrease with time always, they just change up and down. And that's because the relative change of each other. Okay. So how do you understand this result? Okay. So if you observe that the model seems to predict that both population X and Y are periodic in time, this makes intuitive sense because as the number of prey decreases, the rabbits decreases, the predator population eventually decreases because of a diminished food supply. Okay, the foxes, of course, because of shortage of rabbits that foxes need. So the population of the foxes also will eventually decrease, but there is a time delay. They don't decrease on the same pace. Okay, so the decrease of the rapids occur first, and then after some time, the population of the fox also decreases. Okay, but attendant to decrease in the number of predators is an increase in the number of prey. So what it means is, now the population of foxes decreases, but then that will give more chance for the rabbits to survive. So the number of or population of rabbits will, increase after some time, right? Okay. So that means the population of the rabbits decreases first, but then after some time, as the population of foxes decrease, and the population of foxes, the rabbits will increase back. And this in turn gives rise to an increased number of predators. Okay, so because the population of rabbits increase, then that gives us provide more food for the foxes. So the population with foxes will increase also after some time. But once again, the increase will be not in pace with the increase of the rabbits. There's a time delay. So you can see, the population for the foxes also decreases first and then increase. And this which ultimately brings about another decrease in the number of prey. So if the number of foxes increases, or population of foxes increases, then they will need more food from the rabbits. So the population for the rabbits will decrease again. So then that means the population of the rabbits just decreases and increases and decreases. So it's periodical, and similarly, that will cause the population of the foxes also periodic. So that's exactly what we're seeing here. Okay, right? So they are both periodic, but they are not. They're on the same pace, and there's a time delay between the change of the populations. Okay, so the population of the rabbits, the blue curve, decreases first, and then after some time, the population of foxes, the red curve, decreases, and then that will gives the chance for the growth of population of the rabbits. So the population of the rabbits increases, and then because of that, that provides more food for the foxes. So the population for foxes also increased after some time delay, and then because of that, that will consume more rabbits. So the population of rabbits will decrease again. And because of the decrease of population of rabbits, then the population of foxes will also and decrease with some time delay because of shortage of food, and then that again will gives a chance for the rabbits to grow in population and so on. So you can see that this whole curves make sense, right? So that's an interesting phenomenon. So the ecosystem populations more complicated when they have a food chain in the ecosystem. Good. Any questions about this predator prey model? And in the reality, in nature, the situation is much more complicated. When you have multiple populations for different animals, then you have multiple predators and prey. So you will get a more difficult problem to solve. So that's the this model for populations. Okay, let's just continue with some more models with populations. So the population model we just discussed is called the predator-prey model, where the rabbits are the food of foxes. But in some other cases, the two species may not be a predator-prey situation. Instead, they just compete for the food. For example, you have rabbits, and then you have horses, for example. Then they compete for the grasses. They don't eat. They don't take the food for the other species, but they compete for the food in nature. Then we have a different system or different model in that case. So this is called different competition models. So two different species of animal occupy the same ecosystem, not as predator and prey, but as competitors for the same resources. And that includes food and the living space in the system. Okay, that occurs in nature normally. So if each species is diminished by the existence of the other population, okay, because of the shortage of the natural resources, then the differential equations will be like this, will be linear instead of non-linear, but they're coupled. The population of one species will affect the population of the other species. So we have different equations of dx over dt equals ax minus by, where again x and y are the populations of two species competing each other, and the a and b are constants. So you can see. So the first term on the right hand side of the equation just is just from the natural growth or reproduction of the species. But then the other term, negative by, is because of the existence of the other species. The resources are consumed by the other species, and that will cause a decrease of the population of the first species, right? So it's negative. And similarly, dy over dt equals cy minus dx, where c and d are also constants, and that's the exactly similar situation for the population of x. Okay. So they're both just affecting each other, but they are not the food of each other. They just compete for the resources. So this is another model. All right. We already talked about the you know, predator and prey model. So if the growth rate of each species is reduced by the interaction with the other species, okay, that's the predator and prey model. Then we have the equations just we had before. Dx over dt equals ax minus bxy, and dy over dt equals cy minus dxy. This is not actually exactly the same as the predator and prey model. Where if you look at the predator prey model, the first term on the right side of the first equation for the predator, for the fox, is negative because what? Because of the diet. Okay. When there's no rabbits, then the population of the foxes will eventually die out. Okay. So that's the predator-prey model, but now we're talking about a different model when they do have that natural resources in the ecosystem for species X to consume, but at the same time there's interaction between those two species. So the situation is they both share natural resources, but at the same time they have some conflicts between the two species. They may take grass as food at the same time, but then they have competition between the two species for space, for example, and for food, right? So one species will not allow other species to invade its space. So this is a different situation now. Does it make sense? So we have different models, and we have to consider the real situations very carefully, and describe the nature in different models. So that's another model. Okay, so let's just generalize these competition models a little bit. So more generally, the population of each species in isolation grows logistically. Okay, that's more realistic models for the population growth we talked about before. Okay, so dx over dt equals a1 x minus b1 x squared. So that's just for one species. So suppose we just consider the natural growth, reproduction, and the competition inside this population of individuals. Okay, and they have some natural force provided by nature. Okay, but then you have another species. Why? The population will also follows the logistic law. Dy over dt equals a2y minus b2y squared. So these are two realistic models of population without any effect or interaction with other species. Okay, so that's that means even there is only one species in this system, the population will change according to this logistic model. But when the growth rate of each species is reduced by the interaction with the other species, okay, they have competition, they fight. So that will cause the reduction or death of both species. Then we need to add another term of interaction to each differential equation. So we have the two nonlinear equations, dx over dt equals a1x minus b1x squared minus c1xy. And you can factor out a common factor x and get x times a1 minus b1x minus c1y. Now similarly for species y, the equation will be dy over dt equals a2y minus b2y squared minus c2xy. Again, this c2xy is the competition term between the two species. And you can factor out y from the terms on the right to get y equal, to get y times a2 minus b2y minus c2x. Okay, so that's, including the more general situations, that basically includes the competition inside the population or within the species or with other species. If we compare this model with the model, before, we have included both inside also the competitions, but in this model in here, we don't include the competition within the species. Okay. So these are, different models, and we just add more terms to make it more realistic. So you can see when you try to solve a real-world problem, the situation needs to be considered carefully, and you need to modify the model little by little to describe the natural phenomenon more accurately. Any questions at this point about these competition models? If not, then let's just talk about the last thing about this section, the networks. We are talking about electronic circuits, basically. So we also talked about electronic circuit before, but we only talk about the series circuit or circuits in series. Now we have a different situation now. We have networks where you have different loops in a circuit. So a electric network having more than one loop also gives rise to simultaneous differential equations. So in that case, obviously you're going to have more than one differential equations, depending on how many loops you have. Each loop you get a equation. So this situation is shown in figure 3.3.3 in the book. So let's see what it is. So this is the loop or network. So we have the power E, and then this network includes two inductors, L1 and 2 in parallel, and in one branch, we also have a resistor R2 in series with one inductor. Okay, so then we can see, if you consider the flow of the currents, I1 in the major branch, it will split into two branches, I1, I2 and I3 in the two branches, right? And then we can write down differential equations and some other equations to describe the flow of current in the network. So first, the current I1 will be the sum of I2 and I3 because it just splits at point B1. I1 just splits at I2 into I2 and I3 at point B1. Okay. And this is from the conservation of charge. Okay. And then just like before, we can set up a differential equation for each loop. If you consider loop A1, B1, B2, A2, and A1, C1, C2, A2. Okay. So for example, if we just consider loop A1, B1, B2, A2, then E, the power will be equal to the drop of voltage in this loop. So that's I1, R1. Okay, so there's another resistor in the major branch. Okay, so that's the voltage drop in that resistor. And then you consider the voltage drop in the in the inductor. So that'll be L1 times dR2 over dt. So L1 is the inductance for the inductor, and the R2 is the current flowing into this branch. And then there's another voltage drop at R2, okay, in this branch. So they add up, should be equal to the power, okay. The power just supplies this wattage in this branch. And similarly, if we consider the loop A1, C2, A1, C1, C2, A2, you have the wattage drop in I1 also. So that's in resistor R1, so that's I1, R1. And then you only have inductance in this loop. That's will cause the wattage drop of L2 dI3 over dt. I3 is the current in this loop. So that wattage drop will be supplied or provided by the power. So you get another differential equation. Okay. Then we got three equations. Then we can simplify a little bit to change into two equations. So these are the three equations we just had. So if you just plug in the first equation into the other two equations, just replace I1 in the first term of each equation by I2 and plus I3. And then you just combine the terms of I2 in the second equation. Then you're going to get the two equations with I2 and I2 and I3. Okay, so that will be L1 dI2 over dt plus R1 plus R2 I2 plus R1 I3 equals E, and L2 dI3 over dt plus R1 I2 plus R1 I3 equals E. So I just flip left and right for each equation, but you can see if you plug in I1 in both equations 2 and 3, then You don't have I1 anymore. You only have I2 and I3. So that will give you a system of differential equations with two functions or variables, I2 and I3. All right. Any questions for this network? Okay, so I'm going to stop here.